This week the subject is electromagnetic induction. That's chapter 19 in the textbook. For the second part of the screencast, we'll consider AC circuits. So we've already learned about electromagnetic induction and inductance, and now we'll see how that combined with resistance and capacitance behaves in an alternating current circuit. So AC circuit. To get started, let's just think about something that we've seen every day: an electrical outlet, a wall socket. This has a voltage or an electromotive force. It's a time-dependent electromotive force. The voltage difference between the two terminals varies in time sinusoidally. So, for example, it might be some amplitude of oscillation times cosine omega t. Could be cosine omega t, could be sine omega t. Just it has to be a function that alternates or oscillates in time. So the cosine function, let's take as an example, varies between +1 and -1. And so the electromotive force between these two terminals varies between plus V max and minus V max. Now, in America, in the US, V max is 169 volts. The root mean square voltage is 120 volts. It's somewhere between 110 and 120 volts, but as a kind of a standard, we could say it's 120 volts. That's the root mean square voltage. The voltage varies between 169 and minus 169. The average electromotive force is 0 because it oscillates between plus V max and minus V max. So the average is 0. But if you take the square of the voltage, that will vary between 0 and V max squared. And the average of that is the mean square. And the square root of that is the root mean square. The root mean square voltage is 120 volts. Now the frequency is 60 hertz. In other words, 60 cycles per second. The oscillation between plus V max and minus V max, that time, that's the period of oscillation, that's 1 over 60. 1 second divided by 60. 1/60th of a second. One second divided by 60. So 60 of these cycles would take 1 second. Now omega here, which appears in the function, is 2 pi times f. So f is 1 over the period. The unit of frequency is hertz. Hertz is 1 over a second. Omega is called angular frequency. Its unit is radians per second. And 1 complete cycle is 2 pi radians, 360 degrees. All right, well, that's something we're all familiar with. We see that every day. We use that every day. Why? Why does every wall socket in every room in the country have this voltage, this alternating voltage available? Well, this now brings us to alternating current. If you have a AC generator, there'll be an alternating electromotive force. So the alternating electromotive force of an AC generator alternates between Vmax and minus Vmax with a frequency f. That is to say, period of oscillation tau 1 over f. And the EMF, as a function of time, is Vmax times a sinusoidally varying function. Here I've written it as sine omega t. And omega is 2 pi f. So here's a graph of this function. Here's E. The unit of E is the volt. So here is E in volts on a range of minus 200 to 200 volts. This curve is the electromotive force as a function of time. So this is time in seconds. And I've plotted it for 1/10 of a second, 0.1 seconds. The period is 0.0167 seconds. That's 1 over 60. 1 over 6 would be 0.167. 1 over 60 would be 0.0167. So, you know, from 0 to 1/10 of a second is approximately 1, 2, 3, 4, 5, 6 oscillations. Not exactly, but approximately. All right, so the maximum and minimum value of the voltage between the terminals is plus or minus 169 volts. And the root mean square voltage is 120 volts. This red line is the root mean square. The root mean square EMF, that's the average, well, it's the square root of the average of V squared. V alternates between plus or minus 169 V max, plus or minus V max. V squared will be V max squared times sine squared. Sine squared alternates between 0 and 1. The average of sine squared over a cycle is a half. So the root mean square is V max over the square root of 2. And that's the 120 volts. Now, if this generator drives an electric current in a circuit, then the current at any point in the circuit will be an alternating current. I, as a function of time, at some point in the circuit, will be some amplitude of oscillation, that's I max, times sine omega t plus phi. It's also sinusoidally oscillating with the same frequency. So this omega, the omega angular frequency of the current, is the same as this omega, the angular frequency of the electromotive force. Now there's this constant phi. Phi is a phase shift or a phase angle. You see, the current and the voltage don't have to be in phase. In general, the current and the voltage are not in phase. So they're both alternating with the same frequency, but the maximum of the voltage does not coincide with the maximum of the current. So Maximum current, that's the amplitude of the current. Phi is the phase angle. So here's a picture. The gray function is just like over here. The electromotive force is a function of time. The purple curve or function, that's the current as a function of time. And you see it has the same number of oscillations, or the same period of oscillation. You could measure the period of oscillation from the crest of the wave to the next crest of the wave. Again, that's 1/60th of a second. But the place where the maximum occurs is not the same for the current and the voltage. That difference in time between the maximum of the voltage and the maximum of the current, that's phi. Well, not exactly. That's, in terms of time, that's phi divided by omega. So the phase angle in this graph is 90 degrees. In other words, the current and the voltage are 90 degrees out of phase. That's the phase angle for a capacitive circuit. So a circuit in which capacitance is the most important will be 90 degrees, the current will be 90 degrees out of phase with the voltage. And the current leads the voltage. The current occurs first, the maximum of the current occurs first, and then the maximum of the voltage occurs. So we could say the current is sort of lagging behind the voltage. Where the voltage reaches its maximum value, the current has not quite reached the maximum value yet. Now, these constants I max and phi will depend on the resistance, inductance, and capacitance of the circuit. And that's the subject of section 19.5. So be sure to read section 19.5 carefully. Right then, here's a summary of section 19.5. AC circuits. I don't need that. The AC circuit, the AC current to a capacitor leads the capacitor's voltage difference by 90 degrees. So here's a graph of the voltage across a capacitor and the current going into the capacitor. Of course, a current doesn't go through a capacitor because there's an insulating layer, but a current comes into one plate and goes out of the other plate. So this is the current coming into the capacitor. And you see the current is leading the voltage. This is a function of time. So the maximum of the current occurs here. The maximum of voltage occurs a little later. Or if I look over here, the maximum negative current occurs here. The maximum negative voltage occurs a little bit later. So the current leads the voltage. First you have a maximum of the current, then a little bit later you have a maximum of the voltage. The AC current to an inductor lags the inductor's potential difference by 90 degrees. So here a picture of V sub L and I. So this is the voltage difference across an inductor and the current going through the inductor. Well, you see, it's the opposite of the capacitor. Where the voltage is a maximum, the current hasn't reached its maximum yet. The current becomes a maximum at a later time. So the maximum of the current sort of lags behind the maximum of the voltage. Now, we say this is a 90-degree phase difference. In this case, it means that when the voltage is maximum, the current is 0. 90 degrees ahead of leading the voltage. In other words, the difference between the voltage and the current is 90 degrees, or pi over 2 radians, because the maximum of the voltage coincides with the 0 of the current. Or if I look over here, the maximum negative value of the current coincides with the 0 of the voltage. So you see, there's a 90-degree phase difference. I guess we could say the current is leading the voltage by 90 degrees. When the current is 0, the voltage, no, the red line is the voltage. When the voltage is 0, the current is already at its maximum value. Whereas this shows that for an inductive circuit, for an inductor, the current lags behind the voltage by 90 degrees. So if we look at where the current is 0, let's take this point. Where the current is 0, the voltage is at its maximum. So that's a 90-degree difference in the position of the 0 of the current and the maximum value of the voltage. When the voltage reaches its maximum value, the current is only 0. It hasn't reached its maximum value yet. It will reach its maximum value a little later. So the current is lagging behind the voltage. Okay, so that's part of the summary. Now, to be more quantitative, capacitors and inductors have quantities called reactance, which is sort of like resistance, but it also depends on the frequency. Capacitors and inductors also have a phase difference, but let's think about the reactance. The reactance is sort of like a kind of resistance of AC circuits. There's a discussion of phasors as a method of analyzing current and voltage in a AC circuit. The RMS current is the maximum current divided by the square root of 2. The capacitive reactance, call it X sub C, is 1 over omega C. And the inductive reactance, call it X sub L, is omega times L. So the capacitive reactance, kind of effective resistance, decreases as the frequency increases, whereas the inductive reactance increases as the frequency increases. All right, so here are some equations that you're going to need for the long kappa problems. You'll need the equations for the reactances. The capacitive reactance is 1 over omega C. The inductive reactance is omega L. And as for the phase angles, for a capacitor, the phase angle is 90 degrees. And for an inductor, the phase angle is minus 90 degrees. Electrical engineers remember these facts with the mnemonic Eli the Iceman. Eli the Iceman. For an inductor, that's L, the EMF is ahead of the current, or the current is behind the EMF. In other words, the current lags behind the EMF. That's Eli. Eli the Iceman. Well, for a capacitor, the voltage comes after the current. So the current leads the voltage. Voltage comes later. So that's current before voltage, or EMF, in a capacitor. Eli the Iceman. Well, you're not going to be electrical engineers, but every electrical engineer knows the meaning of this phrase, Eli the Iceman. That was section 19.5, which shows the relation between current and voltage for capacitors and inductors. There's also resistors, but we've already studied resistance in Ohm's law. And the phase angle for a resistor is 0. Well, now, having that information for resistors, inductors, and capacitors, we can now go on and study a circuit with all three elements in the circuit: resistance and inductance and capacitance. So the simplest case is just a series RLC circuit. So here we have a series RLC circuit. There's a resistor, there's an inductor, there's a capacitor. And they form a loop, and there's a source of alternating current, which could be provided by a wall socket or any kind of source of alternating current, an alternating EMF. It could just be a generator. It could be a generator, or this could be the generator in the large network of electric wires. It's a source of alternating electromotive force. So that's what's called the series RLC circuit. There's an alternating current generated by the... All right, so that was section 19.5. It describes the reactances and the phase angles for a resistor, an inductor, and a capacitor. Now, section 19.6 considers an AC circuit with all three elements: resistance and inductance and capacitance. So we have a resistor connected to an inductor, connected to a capacitor, and those three are all connected to, or the two ends are connected to, an alternating current generator. Now, to analyze this AC circuit, we use Kirchhoff's loop rule. We say the sum of the potential differences across each part of the circuit adds up to 0. So the EMF plus the voltage across the resistor plus the voltage across the inductor plus the voltage across the capacitor, I've come around in a loop, it's got to be back to 0. It's got to be back to the same point. Or, another way to say it, the EMF must be the voltage difference across the resistor plus the voltage difference across the inductor plus the voltage difference across the capacitor. Or actually, that's the negative of the EMF. Now, because of the phase differences, we analyze these circuits with phasors. We'll have a current with some angle. So there'll be a current in some direction in the phase diagram. And I guess that angle is the phase angle. The resistance, the potential difference across the resistance, will be in the same direction as the current, because there's no phase difference between, for a resistor, the phase angle is 0. But the potential difference across the capacitor will be at 90 degrees to that direction in the phase diagram. And the potential difference across the inductor will be at minus 90 degrees relative to that direction. So the potential difference across the inductor and the potential difference across the capacitor are 180 degrees out of phase. So here's the phasor diagram, or here's a different view of the phasor diagram. We have VR in some direction, and we have VL 90 degrees to VR, and we have VC at, well, VL is minus 90 degrees compared to VR. VC is plus 90 degrees relative to R. VL and VC are in opposite directions. And Kirchhoff's loop rule says VR plus VC plus VL is the electromotive force. So there's the electromotive force. And actually, it's this distance, it's this angle, which is phi. It's not this distance, it's not this angle that's phi, it's this angle that's phi. So Emax is the vector sum of the three potentials. And now let's draw this little right triangle here. I have a right triangle here where the hypotenuse is Emax. The adjacent to phi is VR, and the opposite to phi is VL minus VC. So here's VL minus VC, VR, and Emax. By the Pythagorean theorem, Emax squared is VR squared, and this is wrong. That should be VL minus VC squared. This picture is taken from the book. Well, the equation in the picture is wrong. The equation in the text is correct. Emax, it's just a Pythagorean theorem. E squared is R squared plus L minus C squared. And as for the phase angle, phi, well, just a little bit of trigonometry, the tangent of phi is the opposite divided by the adjacent. The opposite is VL minus VC, the adjacent is VR. So you see, the phasor analysis gives you formulas for Emax and phi. The Emax depends on the generator. It's the amplitude of oscillation of the electromotive force, which is driving the current around the whole loop, the whole series RLC circuit. So this is, again, a part of Section 6, analysis of a series RLC circuit. It mentions that the order of the circuit elements is interchangeable. So I've written it as R, then L, then C, but it could be L, then R, then C, or it could be C, then R, then L. It doesn't matter what order they're in because they're in series. All right, well, again, that's these two formulas. Emax is the square root VR max VL minus VC squared. And you can rewrite that in terms of the current and the reactances. Well, that's something you'll need for the law and kappa problems. And similarly, the phase angle. You might be asked something about the phase angle. Okay, we've already studied this. We can write these potential differences in terms of the reactances. VR max is just the resistance times I max. VC max is the reactance times I max, the reactance for the capacitor. And VL max is the reactance times the current. It's the same current in the resistor, the capacitor, and the inductor. So I max is the same for all three, but the potential differences are different because of the different reactances. For the resistance, it's just R. For the capacitor, it's omega. It's 1 over omega C. For the inductor, it's omega L. And Emax is then a constant times I max. It's kind of like resistance. You know, you can say voltage is ohms times amps. EMF is in volts. I is in amps. Well, volts divided by amps is ohms. So Z is measured in ohms. Z is the resistance. But it's not just the ordinary resistance. It's the resistance plus the reactance, the difference of the two reactances combined in quadrature. So Z depends on the frequency. And then there's also the phase angle between current and voltage. It's the arctangent of VL minus VC, actually XL minus XC over R. All three of these terms are proportional to I max. So I can just cancel the I max and write it as XL minus XC over R. So again, these are the kind of equations that you'll need to do the law and kappa problems and eventually the exam problems. So I hope you're taking notes and writing these equations down in your notebook because you're going to need to use them. Now this leads to an important phenomenon in AC circuits called resonance. First of all, the power dissipated in the resistor is I squared R. But I is varying in time. So the average power, averaged over the time, will be the average of I squared. That's the root mean square current squared times some kind of resistance. But what resistance is it? Well, it's the impedance times the cosine of the angle, the phase angle. So the average power delivered to the resistor is I RMS squared times impedance Z times cosine of the phase angle. Or I could rewrite that in terms of the voltage or the EMF. That's the EMF squared, RMS. Remember, I is E over Z, so this would be E squared over Z squared, so Z over Z squared is 1 over Z cosine phi. Z is called the impedance. It's the square root of R squared plus XL minus XC squared. It's the resistance squared plus the reactance squared combined in quadrature. Phi, the tangent of phi is XL minus XC over R from the previous slide. Now, let's plot this function cosine phi over z, because that depends on the frequency. The reactances depend on frequency, so that means z depends on the frequency. And furthermore, phi depends on the frequency. So let's plot this factor as a function of the frequency. So here I've plotted cosine phi divided by z, that has units of inverse ohms, as a function of frequency, angular frequency, that is units radians per second, for these values of R, L, and C. I took R to be 0.33. I took L and C to be the same, 1 over 2 pi. And you see how the power factor, so this is something that's called the power factor, you see how the power factor has a peak. That's called a resonance. The power factor is largest at this peak. The peak occurs where the angular frequency is 1 over the square root of LC. Or if I take L and C both to be 1 over 2 pi, that would be frequency 2 pi, 6.28. Well, here it is, 6.28. That's the frequency value for the resonance. If you've arranged L and C correctly, then you will be at the largest point for energy transfer from the generator to the resistance. So the resonance occurs for omega equals special value of omega, call it omega sub resonant, 1 over the square root of LC. And that's sort of a desirable circuit, because it means that you're transferring the maximum amount of power from the generator, which is really the origin of the power, to the resistor, which is sort of the load. So you're transferring the maximum energy to the load. At this resonant value of omega, the two reactances are equal. XL is equal to XC. They're both equal to the square root of L over C, because omega is then 1 over the square root of LC. So you see, when L over C, when XL is equal to XC, the impedance is nothing but the resistance. And that's the smallest value that the impedance can have. The impedance must be larger than the ordinary resistance because of these additional resistances due to frequency dependence. But the smallest possible impedance is R, and that occurs at resonance. So this is sometimes called impedance matching. Impedance matching is a desirable feature of, maybe a desirable feature of an AC circuit, so that you have the maximum transfer of energy.